Right. Welcome, everyone. Our next lecture is by Ashia Wilson, who's an expert in machine learning and optimization. Ashia is a faculty at MIT. She did her BA from Harvard and her PhD from Berkeley. Go Bears! And is going to tell us about some of the algorithmic aspects of machine learning. Ashia.
Great. I'm very happy to be here, to be invited. And I wanted to share with you a little bit about algorithms for machine learning. And I'm going to spend the first 15 to 20 minutes situating us in terms of why we care about optimization in the context of machine learning and other things we might care about, just kind of signaling and nodding towards that. And hopefully that'll fold in nicely with some of what's been discussed. So let's first start with what is machine learning. I actually looked up some of the definitions on IBM, Microsoft. Everybody has different definitions, but broadly speaking, I think a good synthesis is that a lot of the definitions say that it's a mix of computer science and statistics, which uses data to learn from examples. But the way I really like to think about machine learning is it's just a procedure that we use to arrive at decisions. This might be a little too narrow for other people's understanding, but I think this captures a lot of what's being done in machine learning. And so the procedure goes a little something like this. Like we have some kind of decision problem in the world. Let's say we want to decide who to hire, if we're part of some kind of institution, or what to major in individually. How much stock should I buy? So as individuals and as part of institutions, we'll be tasked with making many decisions throughout our lives. And the way the machine learning pipeline works is when we start with the decision, we apply this procedure, which means that we have to formulate our decision problem as a prediction problem or something that's aided by decisions, and then use data to generate predictions. And this will be apt and very useful for many, many problems we'll encounter. This is part of the reason why machine learning is super popular. But there are actually going to be tons of problems where formulating this pipeline will result in what I'll call misspecifications. By misspecifications, I'll mean there are ways where this procedure is applied that's going to be based off of normative considerations. It's subjective. We can make many different kinds of decisions, and this gets a little bit into what was discussed yesterday in the context of fairness, robustness, and other considerations we might have. So one example is of a misspecification that tends to happen when we apply machine learning is the use of proxies, and this happens at the point in the pipeline where we're nailing down the data we're going to be using to make the predictions. Very often, in order to do that, we have to specify some covariates and some predicted outcome that we're going to use to make our decisions. And it might be the case, it sometimes is the case, that we'll be unable to assign some measurable value that everybody can agree upon. So some examples would be if I'm some sort of healthcare institution and I want to predict which patients I should triage, for example, I might want to think about triaging those patients that are least healthy. But health is such a comprehensive concept, it's hard to make measurable. So, I might have some sort of markers of health, but that might not capture the full picture of what it is to be healthy. There are other socially constructed variables that often get used in machine learning that have meaning in the real world, but are hard to nail down given they're not invariant across time. They're socially constructed. So this is part, I would say, of this misspecification pitfall where fairness and all this other stuff comes in. It also comes in at the point at which we are trying to make decisions using predictions. I would say three kind of misspecification problems that often arise is the use of prediction itself. Oftentimes we actually need more information, like perhaps causal information, to make certain kinds of decisions, and prediction is not enough, correlation is not enough. Making decisions is really about power, and there's disputes about that in certain contexts, and so that gets written about quite often in the context of machine learning. And then also this pipeline, it's very simplified, and it captures a lot, but often these decisions pipe back into the data we'll see. We're making a sequence of decisions. And so looking at this pipeline statically, there'll be loss, and we need to actually more have a dynamic point of view with feedback. And I think this was mentioned yesterday. So before I dive into optimization and algorithms, I think it's important to understand what this pipeline is doing and how we affix it to different problems and what we should be wary of. The last thing I think that ought to be mentioned is there are also errors that occur within this pipeline. And by errors, I mean, these are errors inherited in the paradigm or from the paradigm of just simply learning from data. So even if our decision problem can be well specified using this framework, just by learning from data, we'll probably make the errors. And what I mean by that is that in this ideal setting, how will we learn by example? Well, we would see all the examples of the thing we're trying to learn about. So let's say all possible species of dogs, if what we're trying to predict is the labeled dog. And ideally, we'll have this prediction function that's flexible enough to actually predict or discriminate across dogs and everything else in the world. So it'll be very flexible, and this is just a well-defined problem. And however we're using this in our decision-making will be somewhat straightforward. So this is the ideal setting where machine learning is just perfectly matched or suitable to our decision problem. But in the real world, we don't get to view all the examples, and you probably have heard this story. This is the story of machine learning. We're learning using only a subset of examples. And so this mapping from this ideal setting to this real setting will create certain kinds of errors, or can create certain kinds of errors that might pipe through to our predictions and our decisions. Also, it may not be the case that the prediction functions we're trying to learn could even discriminate, even in the ideal setting, across all the examples. And so this leads us into, finally, the topic for today, which is going to very much zoom in and concentrate on how do we learn predictions from data, from subsets of data. And so I'm going to discuss a little bit the ins and outs of how this is done in practice and some very basic templates of algorithms that I think you guys should know about because they are used all over the place. But in this realistic such situation, recall this framing, we have this X and Y variables, which I'm describing as these covariates and this predicted outcome. And the goal is to predict the outcome from these covariates and ideally use these predictions in some sort of ensemble or via some sort of thresholding rule to arrive at a decision. What is the optimization piece? How do we actually arrive at these predictions? One of the prevailing paradigms in machine learning is a technique called empirical risk minimization. And so the idea of this, we're going to define what I'm going to call a empirical risk function. And it's just going to sum over this function, which is the loss function, between my prediction function evaluated on the covariates and the measured outcome. And so the idea here is this loss is going to count the match, or going to qualify the match between these two things. And I would like to find the prediction function that minimizes this objective on at least the data I'm seeing now, with the hopes that this will discriminate well for the data I will see in the future. So I'm going to revisit this, why we care about this, why this is a good objective function to perhaps minimize. But I do want to point out a couple other things that people in the TCS space really care about that won't be addressed here, and I think is just equally as important, if not more so. The first idea is this idea of generalization. Sadly, this mini course is small enough so that I won't be able to capture too much of it, but the idea of generalization is this. So we have this, I said, realistic setting, and we have this ideal setting. And we're using this principle called risk minimization, or empirical risk minimization, to arrive at a prediction function using finite data. But the same procedure could be applied in principle to all the data. And so that's what this objective function is representing. So this is what's called the risk. It's the loss evaluated essentially on all of my data. And I want to find the prediction function that minimizes this loss with respect to all the data I could possibly see. And so generalization really concerns itself with trying to classify what is the gap between doing this on a finite data set and doing this in this ideal setting. So this generalization error is generalization error for a prediction function. Typically we care about the average generalization error. And this gets into all sorts of wonderful, beautiful topics like VC dimension, Rademacher complexity, pack phase, margin bounds. I would love to unfurl some of these in this setting, but unfortunately, we don't have time. But I encourage you guys to take a learning theory class. And so what these things are doing is trying to get at the complexity of this function class so as to bound this generalization error. Just very loosely speaking, I won't say much more than that. But other things we do care about are also approximations. So how expressive is this prediction class, this class of predictors I'm using? Can it classify anything, any data I throw at it? How expressive is it? This definitely comes up in the context of neural networks, where there are nice approximation theories for super wide neural networks. Again, I'm not going to be discussing approximation as much, but it's very important, I think, if you're trying to take a comprehensive view when thinking about how things work. And the final thing that I won't be getting to, but that TCS people, I think, very much care about is representations of the data. Thinking it through, what is a good representation of the data and what is the structure of just the natural data you're seeing. It's important to discriminate natural data sets from arbitrarily or artificially constructed ones and kind of understand what that structure is. And I think that gives insight into ideas such as generalization and other things here. So all these topics tie together. They're all very, very important. But today, via this long introduction, we're going to really narrow down into the optimization land and focus on, okay, how do we minimize the empirical risk? This objective function is used to train all sorts of machine learning algorithms, all sorts of machine learning prediction functions that we use. So it's important to understand this framing and some of the algorithms that are popular and used. And I want to make sure we understand that the focus for a lot of people coming from TCS is this two things: the computational resources needed to find F hat and the wall clock time required to obtain a good prediction function. So how many, that usually translates into also how many iterations do you need, how many, if I'm applying an algorithm, to find F hat. So that is what we'll be considering today. But before I dive into just kind of the broad picture, I do also want to make a plug for taking an optimization course. If you guys are going to continue in TCS, I really think optimization really appears throughout many topics, including other TCS type topics. It really is a universal language for formulating problems and solving them, and it shows up in engineering, econ, biology, physics. This is just to name a few. And TCS as well, a lot of times progress is made by relaxing problems into optimization problems and finding approximate solutions. It's very, very much a leading paradigm. I'm going to give you maybe what you would encounter in the first couple of weeks of an optimization class and hopefully give you some problems that will help stimulate some ideas you guys might have. So with that, I'm going to switch to my iPad. So give me 1 second as we go into some more details about optimization algorithms. So let me do that. Let's see, this is going to work. Okay, hopefully, oh, did that work? You guys see? Okay, fantastic. I think I see it mirrored, so I'm happy. Okay, so we're going to kind of write a little bit now. So So we're talking about optimization, and as I discussed, it's used to learn a prediction function from data via this procedure called empirical risk minimization. And nowadays, the problems that we care about are very complex. And what do I mean by complex? I mean that they often require solving a non-convex problem. And so we'll get into convexity, non-convexity a little bit today, but the basic separation I'm talking about is it falls into this class of problems where we don't have strong guarantees about finding the solution. And that's an interesting demarcation. And of course, non-convexity is a huge class of functions. So it's almost meaningless to discuss it very generally, but it is important to understand whether the function you are trying to minimize is convex or not. So in this mini course, we're going to discuss some of the classic theory of optimization for a couple of reasons. Even though that some of the leading research is on non-convex optimization and extends beyond these boundaries, a lot of the ideas being applied, a lot of the theoretical results still draw, I would say, in large part on intuitions stemming from the classical theory. And so having a grounding in this is super important. Okay, so with that, let's go into convex optimization a little bit. So what do I mean when I say a function is convex? Well, a function is convex. Let's say my function is Rs. I'm suggestively denoting the function as the empirical risk. It's convex if Rs of lambda x plus 1 minus lambda y is less than or equal to lambda times Rs of x plus 1 minus lambda Rs of y. So that's one definition. And this just simply means that the line connecting 2 points on the curve lies above the curve. So one can think about a nice parabola here. Let's say we have 2 points. The line connecting the 2 points should sit above the function evaluated anywhere along the between the 2 points. Another definition that is quite often used and very useful is that if you have a differentiable function, you can define convexity in the following way. So Rs of y is going to be greater than or equal to Rs of x plus the gradient of Rs of x times y minus x. So that's another definition of first order, they would say, definition of convexity. And the last definition a lot of people use is if you're a twice differentiable function, then being convex simply means that your Hessian is positive semi-definite. So the Hessian, sorry, Rs of x is going to be PSD. Okay. So given a convex differentiable function, what we want to find is a point x star such that, or really, sorry, we want to find a point x such that Rs of x minus Rs of x star is less than or equal to epsilon, where x star, let's say, is in the argmin of Rs. So it's one of the minimizing points for our function. So we're trying to find a minimizing point, but we'll say it's sufficient to find a point such that when I evaluate the function at that point, I'm arbitrarily close to the minimal value of the function. Okay, so I am going to claim that convex functions are super nice. The reason why we deal with convex functions there are many reasons. The first is that the local property which is, sorry. Which is that the gradient of my function evaluated at a point being 0 implies that X is a global minimizer. It belongs to this global minimizing set. So that's really nice. Normally I would have to, if I'm thinking, if I'm in, I have an arbitrary function and I want to certify that at a point I found is minimal, what I would think to do is check every other single point and compare it and make sure its function value is smaller. But for convex functions, it's just sufficient to check that the gradient evaluated at that point is 0. And then I just have a certificate of optimality. So that is probably a key property, the key property that makes convex functions incredibly nice. Another property is that the sublevel sets of a convex function are convex. And what do I mean by sublevel sets? This is going to be the set D, which consists of all points such that Rs of X is less than or equal to C. So this would be D sub C, and for all D sub C, these trace out convex sets. And this is a nice property to have. Why is that? So let's see. I argue that these two properties really naturally suggest an algorithm that will find minimizers of our convex functions quite quickly. And the algorithm we're going to discuss today, the main one, is called gradient descent. Some of you guys may have heard of this algorithm, but for those of you who haven't, it's very, very good to understand this algorithm. You might be asked to apply it in whatever job setting you have in the future. So what is gradient descent? Well, it starts by initializing a point, or any random point in the domain. And then for each iteration, what it does is it updates your current point. So here I've switched the variable from X to W, so my apologies. So I update what I'm going to suggestively call the weights by taking the current state and subtracting the gradient times this parameter eta. And so eta is often called the step size. Okay, so why would these two properties of the gradient being 0, being a global certificate of optimality, or these sublevel sets being convex, imply that this algorithm might be useful to use? Well, so first of all, it's important to think through what the gradient is. So the gradient is perpendicular to the sublevel sets of the function. So let's look at this graph here. So these blue curves that I've traced out are going to be the curves of W, the sublevel set. So W such that Rs of W is equal to C. So this is for each C, C prime, C double prime, and so forth. The gradient direction is going to be perpendicular to the sublevel sets. And furthermore, the gradient is going to point in the direction of steepest ascent. And conversely, the negative gradient will also be perpendicular to these sublevel sets. It'll point in exactly the opposite direction, in the direction of steepest descent. Another thing that I think is going to be very useful to point out is, let's say I run this algorithm and I keep running it. At what point does the algorithm stop updating the parameter W? Oh, I should also say that eta has to be, we're going to restrict that to be strictly greater than 0. So it cannot be 0. So at what point will the weight stop being updated?
When W is less than epsilon from the optimum?
Yeah, exactly. And why is that?
Because at that point, it's just kind of circling around the optimum.
Yeah. So importantly, as Alexander pointed out, this algorithm will stop. So WT plus 1 will equal WT precisely when the gradient here is equal to 0. And based on this local property of the gradient of S being 0 exactly when I'm at a global minimizer, this algorithm will stop updating, or will just stop updating when I'm actually at a global minimizer. And therefore, I'll get this certificate here that I've reached a point such that I'm epsilon away. And really here, epsilon will be 0 if I'm really not updating at all. So that's really nice. I mean, it really, this local property implies that gradient descent would be a smart thing to do. If I just keep updating and just stop when I have the certificate of optimality, then I'll find, maybe I have to trace out the entire space, maybe be horribly inefficient, but eventually I will have this certificate, I will find this point. So the intuition is just simply to move in the direction that decreases the objective function the most. And I told you guys this could be inefficient, but it turns out for convex functions and other function classes, this actually isn't going to be too inefficient. It will find a minimizer quite quickly. So one of the first questions I want to ask is the objective function actually decreasing? So if I run gradient descent and I choose eta, to be some value and I keep updating, will the objective function always decrease? So if I evaluate the objective function, I keep evaluating it at every state, from state to state, will my function value be decreasing? And to answer this kind of question, we need some other conditions. This will allow us to figure out in which cases I'll always have function value decrease, and also help me to discern how fast the objective function is decreasing. And so one of the more important properties that many objective functions have is this property called smoothness. So what is smoothness? We say that a function Rs is L smooth if the gradient of Rs evaluated at X minus the gradient of Rs evaluated at Y is upper bounded by some constant L. That's where the L comes in. It's the distance between X and Y. So that is what it means for a function to be L smooth. If Rs is twice differentiable, this condition is just simply an upper bound on the second derivative of the gradient. Second derivative of the function. So it simply says that I have this condition for all X in, let's say my domain is RD. Okay, fantastic. One other property that comes up quite often in the context of optimization, perhaps not deep learning or non-convex optimization, but an important property nonetheless, is this idea of strong convexity. And so what does it mean to be strongly convex? We say that a function Rs is mu strongly convex if Rs of Y is greater than or equal to Rs of X. So what I've just written down so far is the property of being convex. Convexity means that the linear approximation will always be beneath the function. Strong convexity adds this quadratic term. So it's this condition that implies you can always fit this other quadratic term in this linear approximation here. So that's a little bit stronger than our normal convexity condition. If mu is 0, then we have convexity. But mu being strictly greater than 0 is this nicer property. So strong convexity, this condition can be written in a variety of different ways. If you are twice differentiable, this is simply a lower bound on this Hessian. But another property, or something we're going to use when thinking through how does gradient descent and stochastic gradient descent and a couple other algorithms, how do they behave, is that strong convexity implies that the gradient is a lower bound for the distance between the objective value evaluated at x and the objective function evaluated at one of the optimal values. I should mention that if you have a strongly convex function, it means that you only have one unique minimizer. So it's a much stronger condition than general convexity. But this is a really nice property to have, and we'll see why in a second. Okay, so I'm going a little bit fast. I'm not quite sure how to calibrate how much people have seen, how much to get through, but if I'm going to pause and take questions in case there are any.
Could you? Sorry.
Yeah. Oh, sorry. What? Yeah, Ran. You can go, or I forgot who else.
Yeah. Okay. So, can you just repeat what the last thing you wrote means?
Oh yeah, of course. So, do you mean this, or do you mean this?
No, the later one.
Okay, later.
Lower.
Lower. Oh, this. Wait, I don't think I've gotten lower than.
The like this also implies this one.
Oh yeah. Okay. Oh yeah. Okay. Great. Okay. I was pointing out the right thing. So this condition is something that is implied by strong convexity. We can actually, I think maybe on one of the worksheets, I ask you to show this fact. So I may not prove it right here. So this condition is that the gradient evaluated at any point, in some sense, gives us a measure from how far we are from an optimal point x star. And actually, this condition, I should mention, is weaker than strong convexity. And in fact, non-convex functions can satisfy this condition. But it turns out this condition is going to be sufficient for obtaining fast rates of convergence, or showing that gradient descent finds minimizers quickly. So I may not have needed to trace through all of strong convexity to write down this condition, but this is an important condition, and I want to at least table that and tell you guys it's called the Polyak-Lojewski. I cannot pronounce that. The PL inequality. If you Google PL inequality, this will come up. It's a very complicated last name that I always butcher. It's an important condition in the context of optimization. It also comes up in other spaces as well. So this is going to be sufficient, perhaps necessary condition for linear convergence. I'm not quite sure about the necessary, but certainly sufficient for a rapid convergence. Right. Were there other questions? I think someone also, and Rand, did that answer or clarify at least?
Yeah.
Okay, good. Were there other questions?
I was just finding it a bit difficult to believe the strong convexity exists. Could you give an example? Because it looks like it's pretty, like the gap is pretty big between RS and RY.
Yeah, so strong convexity, let's see. When you have a quadratic function, for example, and let's say ax squared, in one dimension, ax squared plus bx plus c, or ax squared, let's say, plus bx, and a is positive. Then your function, you can check, you write down what the gradient in the, or even just the Hessian is going to be a. So as long as a is positive, you're going to satisfy this lower bound here. And you can do this in more than one dimension. So if I have x transpose ax, let's say, and that quadratic function is also going to be, as long as a is positive definite, this is going to be strongly convex. Actually, in general, if I add a small quadratic function to a convex function, all of a sudden that function becomes strongly convex, with the scale of the quadratic I added being the strong convexity parameter. I actually think that might be part of the problem in the problems I gave to you guys. So there are quite a few examples of strongly convex functions that are used throughout machine learning. But also, as I said, the PL inequality is going to be somewhat sufficient for ensuring that gradient descent will find a minimizer quickly. So even something weaker than this lower bounding quadratic will suffice.
Okay.
Yeah. Great question, though. It's good to see more examples. So I apologize, I haven't gone through too many quite yet, but I think we'll get there. Okay. So I've introduced a couple of concepts. So one was the notion of convexity. The motivating force for convexity is, these are functions where I can find minimum values, and often quite quickly. And then I have these other two concepts. One is called smoothness. It's an upper bound on the Hessian if I'm twice differentiable. And I have strong convexity, which is a lower bound on the Hessian if I'm twice differentiable. So why introduce all these concepts? Well, smoothness is super important because it controls how you choose the step size, and it gives us so we should choose a step size based on the smoothness parameter, and it also is a sufficient condition for finding, let's say, minima of convex functions quite quickly at a polynomial rate. So let's check that this is true. And then hopefully we can build off this result to establish some other things, even in the non-convex regime. So the lemma that we're going to trace through is the following. So let's say I have an objective function, and it's L smooth. So this is the condition on the gradients, or I can write it as a condition on the Hessian. And let's say that step size eta, so this is going to be greater than 0, but less than 2 over L. Then along gradient descent, I'm going to have, let's see, did not write this all out. So along gradient descent, I can show essentially that my objective function here is decreasing. So this is what I'm hoping to show. That the objective function evaluated at the next iterate of gradient descent is going to be lower bounded by the objective value evaluated at the current iterate minus something that I will hope will be positive, so that I can just say that the objective function is decreasing at every single step. Specifically, if I choose eta to be less than 2 over L, then this part here will be positive, and subsequently, because the norm of the gradient is positive, I will guarantee that I'll get objective decrease. So that's where this condition comes in. And if I optimize kind of how do I choose eta given this equation, people typically choose eta to be 1 over L, in which case I can say I get this amount of decrease. So again, let's take a pause. So I have gradient descent. Intuitively, I'm marching in the direction of steepest descent. But there are contexts, let's say I let's do an example. Hold on one second. Okay, so let's say I have sub-level sets that look like this. And I start right here. And the minimum is right here. If eta is super large, what could happen is I could overshoot this minimum. Let's see. I hope I drew that perpendicularly. I didn't really. So let me just draw that again. It's perpendicular to the sublevel set. So it's going to be X. So I go here and I might overshoot it. This sublevel set might point me in this direction, but if I take too large of a step size, I just overshoot the minimum and I could keep bouncing back and forth and never reach the minimum value. So it's important, the step size, and you'll see if you ever implement gradient descent, it's going to be super important for making sure that you actually converge to the minimizing value of your function. So, and it turns out that the condition we need is, or a condition we'll need is that your function has smooth gradients and that the step size should be chosen in proportion to that smoothness parameter L. So if you do that, then you're guaranteed to decrease at every single iteration. And let's prove this fact. It's a 3-line proof. So the first thing we'll write out is this definition of L smoothness. So a function being L smooth means that this first order approximation to the function at RSWT plus this quadratic, so sorry, this first order approximation is upper bounded by this quadratic, where the scale of this quadratic is this parameter L. So here I've just pushed this hyperplane on the other side. So this is another way of writing this smoothness condition. So WT plus 1 minus WT, if I look at gradient descent, this is going to be the negative gradient of my objective function at WT. And similarly, I'm going to plug that in here. So this is where I'm using the property of the algorithm. So I plug in that value of the algorithm. And what this tells me is that now all of a sudden, the distance between RS of WT plus 1 and RS of WT is going to be upper bounded by something that I can measure in terms of the gradient of RS at WT. In particular, if I collect terms, I have this one eta term here, and then I have another eta term here. So let me pause again and make sure that was somewhat understood. So a couple steps, just use smoothness and then plugged in the iterate of the algorithm. And that allowed me to establish that essentially I get a decrease that can be measured by some scaled norm of the gradient. And hopefully that scaling parameter is going to be positive so that it is in fact decrease. And that scaling parameter being positive is just subject to how I choose eta. Okay, so this is just basic. All of a sudden, I've got this descent condition. So this is really nice for several reasons. So first of all, what if I have a non-convex function? I don't have convexity. Note that this condition here only required smoothness of my gradients. And I can ensure that the objective function is decreasing. So the objective function for gradient descent, if I have smoothness and I choose the step size nicely, will always be decreasing. And it will only stop when the gradient, or stop updating when the gradient of my function is 0, evaluated at that point. So for any arbitrary function, if I run gradient descent, it'll decrease my objective function and only stop at a point for which the gradient is 0. So let's say my function looks like this. And let's say I start right here. Well, if I keep going downhill, essentially, let's say keep marching downhill, all of a sudden I'll only stop right here. This is going to be where the gradient of my function, I'm calling my function RS. So let me stick to that convention. So this is RS of X. The gradient will also be 0 here and will also be 0 here. It'll also be 0 here. So if I start here, I'll never move. And it'll also be 0 here. There are also going to be inflection points. I haven't, I think this will be an inflection point. There'll be, sometimes there are inflection points. I actually didn't draw this quite well. Should have drawn a more kind of complicated function. But the point being that, or saddle points, there'll be points at which the gradient is 0, and there'll be either local maxima, local minima, global maxima, global minima, or these things called saddle points. So if I run gradient descent, I'll find one of those points. And this ends up being really important as we think about how algorithms behave, let's say in non-convex land. Will they actually converge to these saddle points? They'll only converge to these maximal points if I start there. So that typically will not happen, but and then which local minima? Well, it really depends where I start the algorithm. Okay, so taking a step back, gradient descent is nice. We use it to minimize or find solutions to non-convex problems because we are guaranteed that we'll find critical points for them. And often these critical points will be local minima or sometimes global minima. But for convex problems, they're even nicer. So I want to summarize the non-convex land by saying finds critical points. I haven't told you how quickly it will find a critical point, but it will find a critical point if I just keep running it. But it will find minima of convex functions and strongly convex functions quite quickly. And so this is where this strong convexity condition, or really even the weaker property of the PL inequality comes into play. So I've just established this condition here. The function value is decreasing at a rate measured by the gradient. But strong convexity gives me the property that this gradient, sorry, this should be negative. This negative gradient, sorry about that. When I post these notes, make sure all is edited. This is the condition. Sorry. Let's go back here. So strong convexity, it gives me the condition that the negative gradient is a lower bound for the negative gap between my function and the function evaluated at the optimal value. So essentially, I have that this is yeah, I actually wrote this down correctly. When I first glanced at it, I was like, did I write that down incorrectly? But I didn't. So this is going to be 2 mu eta 1 minus eta L over 2 times RS of WT minus RS W star. And if I plugged in, so then I've written this down, or so I can rearrange and obtain this statement, but let me show you how you do that. So let's apply this shorthand. E of t is going to be RS of WT minus RS of W star. So if I take this convention, what this is saying is E of t plus 1 minus E of t is less than or equal to RS, so negative 2 mu eta times 1 minus eta L over 2 E of t. Right, so I need that to be negative. Or ET plus 1 is less than or equal to 1 minus 2 mu eta, 1 minus eta L over 2 ET. Right, so I did actually do that quickly. So does that make sense to everyone? Sorry, this line's kind of in the way. I'm going to pause here, make sure everyone understood each step. So I have this statement here. I added and I subtracted RS of W star. This allowed me to write these two, the difference here, as ET plus 1 minus ET, because the RSW stars cancel. And I just get the difference in the function values. And again, ET is also this term here. So I just simply use this notation to rewrite this inequality. And then I dragged in this final step the ET to the other side. Is that, yes, Fran, there we go. I knew there would be questions.
So this K, like, what is the K?
Oh, what is the K?
Yeah.
Oh, yeah, sorry. I often, when I write iterative algorithms, I use K to index it. This should be T.
Okay, thanks.
So yeah, so what you do, okay, so ET plus 1 is some scaled version times ET, then I say that's some scaled version times ET minus 1, and I keep unfurling this, and then I eventually get this thing to the Tth power times E naught, which I'm calling here, I suppose I start at W1. So did those steps make sense to everyone? So 2 things. I have smoothness, I find critical points. I have smoothness in this strong convexity condition, or even weaker than strong convexity, and I find this minimal value, or I can bound how close I am by some scaled version times my initial distance here, where the distance is evaluated by the function value. So all I need is
I'm assuming that either a device died or a connection got lost. So I expect that she'll be back in a moment.
hi, hello.
Hi.
Oh my goodness, I don't know what happened. I just got kicked out.
Oh no.
I'm so sorry. Okay, let me continue.
Great, thanks.
Yeah, of course. Sorry about that, everyone. Let's see. Let me share my screen. Okay. I'm so sorry, everyone. I don't, getting kicked out. All right, resharing my screen. Please. And okay, are we back?
Yep.
Okay, fantastic. And the last thing I have to do is start my video so everybody can see me. I really apologize. Technical difficulties, I guess. Hopefully that does not happen again. And okay, so we were in the midst of kind of drawing this final conclusion for gradient descent, which is that for nice functions that have this property of the gradient being a lower bound for this gap, we converge at a linear rate. And specifically, if we choose eta to be 1 over L, then the rate at which we are kind of converging is going to be 1 minus mu over L. Mu over L is typically referred to as the condition number. Why is that? That's because if we are quadratic, so remember, mu is this lower bound on the Hessian here, and L is this upper bound on the Hessian. So if we're quadratic, the Hessian is just a fixed matrix A. Let's say if I have an objective function x transpose AX. And so this is precisely the condition number of that matrix. So this is, I'm converging at 1 over the condition number. The condition number is usually referred to as K or L over mu. It's okay. I just want to introduce you guys to that kind of common notation, but let's go back. So, okay. The last thing, or the last concept I want to draw your attention to is stochastic gradient descent. So we have this algorithm, gradient descent, and it essentially computes the gradient at every single iteration. And so let's look back at our empirical risk minimization problem. Our empirical risk minimization problem is to compute the gradient of RS, let's say of W, I have to compute the gradient of this loss function with respect to W. And I have to sum over all of the weights. So if n is super, super large, like in common deep learning contexts, this is going to be quite expensive to do. So for every iteration, I have to compute the sum over n. So if n is like, 1 million, this is going to be almost impractical to implement. So there are several techniques for getting around this difficulty. And the most popular of which is called stochastic gradient descent. And so what is the basic idea? Instead of computing the gradient and going in that direction, I instead approximate the gradient direction using a randomized procedure. And this randomized procedure should, in expectation, move in the right direction, move in the gradient direction. Okay, so what is this randomized procedure? So SGD has the following update sequence. I start at any initial point, and then I, at every iteration, choose I being one of these points, uniformly at random. So 1 through n uniformly at random. And then I compute the gradient of this loss function L, evaluated only at the random point I chose. So now, instead of when I compute the gradient having to do this for every single I, and then therefore the gradient computation requiring me to perform this expensive operation, I now have something that's substantially cheaper if n is really large. This is what's called stochastic gradient descent. And because I'm choosing this index I at random, then if I take the expectation, so if I compute the expectation with respect to this selection procedure here of my gradient, this is going to be the gradient direction. So I'm just going to say gradient of RS of W. So it'll be an expectation. I will compute the full gradient, but this is a randomized procedure. So people, when they're implementing stochastic gradient descent, don't just select one point uniformly at random, but let's say a group of K points. This is what's called a mini batch. And they evaluate the gradient at those K points here. And so they use that as an estimate of the overall gradient. So K is typically substantially less than N, but maybe greater than 1. It's however much your computer can handle, it's somewhat reasonably. And so the basic idea here is, well, so now I'm choosing a random gradient. This is a random variable. In expectation, it's going to be the gradient. So if I'm thinking of it as a random estimate of the gradient, it's unbiased. But it also has a variance, right? So that's going to be, it's going to be the expectation of u squared, or the gap squared. And so the idea here is that if I choose K to be larger, that's going to reduce the variance of the estimate of the gradient I am using. I still get an unbiased estimate, but the variance will be reduced. And if K is N, then there is no variance because that is essentially the gradient. All right, I'm going to pause here and make sure people understood this point. So you have a problem you're trying to solve. It's an optimization problem. And oftentimes, this is going to require taking a gradient which involves summing over the data. The dimension of the gradient is also going to be sometimes a problem. And there are tricks around handling, doing the full dimensional computation. But here, when n is large, what could we do? And so the basic idea here is to estimate or approximate our gradient with fewer points. And that will allow you to run your algorithm on your computer and not need a cluster or a GPU. I mean, you probably will still need to use a GPU because you need to actually store all those points somewhere, and it's quite complicated. But this is what is commonly done. Okay, so again, I want to pause and make sure it was understood kind of some of the basic properties of gradient descent and some of the basic properties of stochastic gradient descent. Any questions?
It looks like there's a question in the chat. I can read it aloud if you like. If you had priors on the relative predictive power of different features, would it make sense to sample the coordinates non-uniformly?
So there is a way to incorporate that prior information. I don't think the relevant procedure, as far as I know, is to do that, to use it in the sampling of computing the gradient. Typically, the way we do sampling might involve the Lipschitz constant for every single point. So if I have, so each stochastic gradient might be L Lipschitz, depending on where L depends on like the point it's evaluated on. And often the scaling of my step size I might want to vary that depending on the Lipschitz parameter of the function evaluated on that specific point. But if I had a prior on the predictive, yeah, it's a little hard to disentangle because it really depends on your model, your loss function, the structure of your loss function. It's unclear in the context of neural nets. You're trying to solve for the weights. You might think that some weights are going to be bigger than others, and there are other ways of incorporating that. But yeah, I don't think that that's something that's typically done.
And then there's another question in the chat, which is, what if the objective function cannot be expressed in a finite summation?
Oh yeah, so what if you're minimizing something that is an expectation, like an integral? It's not a finite summation. So in this context, I'm hammering down to empirical risk, but for example, the risk function itself is the integral over all of the data, and therefore cannot be necessarily expressed as a finite sum. There, typically, you assume you have oracle access to a random sample of from your distribution, or a random draw, some kind of random draw from your distribution, and that you can express SGD more abstractly. So instead of gradient of L evaluated Li, let's say, we have the gradient of L evaluated at some oracle that gave me a random draw from my distribution. And that would be a stochastic gradient. If you don't have either, that's going to be a little bit difficult. I mean, you might actually, yeah, I'm not quite sure. I'm not quite sure in what context you would at least have some sort of access to a random sample. Or yeah, so that's a little bit difficult. But notice when we draw inferences about the convergence of SGD, it's not going to depend on, abstractly speaking, it won't depend on large N. I mean, it will insofar as, yeah, we can draw inferences that won't depend on N being finite. Yes.
Okay, yep, and we have another question in the chat, which is, are there any learning algorithms that are even cheaper computationally than SGD that can still be useful in practice?
Yeah, so there's this thing called zeroth order optimization. And so the idea here is that instead of using gradients, computing gradients can be quite expensive, we can just compute function values. So as long as I have access to just the function value evaluated at some point that I, let's say current point I have, then I can use that and let's say some previous point to get a first order approximation of the gradient. Typically have to like convolve that with a Gaussian or use a Gaussian draw there, but that's significantly cheaper. And you can get guarantees about finding minima for certain kinds of functions with zeroth order optimization. The guarantees are going to be weaker than, of course, if you had full gradient access. But that's a pretty thriving field. So yes, you can do something less expensive. Now, unless you know something more about the structure of your problem, if you don't even have function evaluation access, then it's going to be a bit harder to develop a procedure to find the minimum. You could always partition the space and do a random search, but then that's going to scale horribly with the dimension of your space. So that's a little bit untenable, but that's definitely a randomized procedure that eventually you will find the minimum. Eventually being maybe like the time of the universe, but yeah, eventually. Let's see, any other questions? These are good questions. Learn a lot about kind of what was clear, what was not clear based on what was asked or what is asked.
Yeah, there's another question. In which type of setting is it realistic to use gradient descent or even stochastic gradient descent?
Yeah, fantastic. Think a rule of thumb that may or may not still, I think it's still useful today, is if you can fit all the data on your computer, then you might as well just run gradient descent. That's kind of, I mean, so one thing you want to do is gradient descent, the guarantees you'll find are going to be significantly better. It will find the minimum faster. So we just proved a linear rate. In the problems I gave you, you'll find that SGD stochastic gradient descent will find the minimum at, let's say, a rate of 1 over the number of iterations. So that's weaker by quite a bit than gradient descent. So it's just a matter of how expensive is it to compute a gradient and versus how many iterations you need. And so the rule of thumb is if it's not too expensive, i.e. your data set is somewhat small, perhaps fits on your computer size, then gradient descent is worth running. And if you're in the regime of, if you're in the big data regime where you kind of need multiple clusters, then SGD is definitely the default, what is used. And I should, the one other thing I want to say is these two algorithms are like the basic templates, but typically the way things have gone is a lot of algorithms get developed to minimize convex functions, and then a lot of them, some larger subset of them, seem to work in the non-convex regime. So I want to also hammer in that it is worth understanding this more classic setting well, if you're thinking about optimization in a more modern, perhaps non-convex setting. Are there any other questions?
Yep, there's a, what about parallel gradient descent?
Yeah, I didn't get into a whole bunch of stuff. I'm hopefully going to touch on it in the next, on Friday. There are tons of things that can be evaluated. So parallelization, projection. So let's say I kind of hid the set that, let's say, the weights live in, but let's say it belongs to some sort of convex set. Then a problem with doing a gradient iteration is you can march out of that set. There's this thing called projected gradient descent. There are other techniques or other modifications of gradient descent to adapt to more modern settings. And they're typically, it's worth understanding how to modify the basic analysis template, but I would say there is kind of some sort of standard analysis template that pretty much, if you're trying to understand it, there's a kind of more systematic way as you kind of get more into these settings. But yeah, parallelization can be somewhat analyzed, or can be analyzed, and it's, like I said, I might get into that in the next, on Friday.
Got another question, which is, do you have any recommended readings, textbooks on optimization ML algorithms?
Oh, wow. I want to include everybody. So it's going to be a bit hard. Let's see. I really still love Stephen Boyd's convex optimization, but it's like huge textbook. It's very comprehensive and it gets a little bit more in the classic. It's less ML based, I would say, a little more classic SDP, LP, linear programming, quadratic programming kind of stuff. But I think what it does touch on, what I didn't really talk about as much, is modeling. So I have some abstract problem. In a lot of settings, I want to model it as an optimization problem. So how do I kind of formulate it as one of these nice quadratic programs, a semi-definite program type stuff? So I think that book is really wonderful. Oh boy, I will shout out my advisor. He just wrote a textbook on, over to my PhD thesis advisor, Ben Rex, just wrote a textbook more or less on ML, but there's a somewhat sizable optimization component in there. And I think his viewpoint obviously is shared a little bit with myself, and he was my advisor. And I like the connection between algorithms and dynamical systems. I'll get a little bit into that on Friday. So I think that textbook is called An ML Story. If you Google Ben Rex, I'm pretty sure Benjamin Rex is at Berkeley, and there's a link. And Moritz Hart is also an author on that book. Let's see. I'm forgetting other people though. There's some convex optimization type books that are aimed more at, let's say, online learning. I think Sebastian Beck has a nice book that really lays out all the theoretical results. I mean, if you're really into the theory of this stuff, that's kind of like a nice resource, go-to resource. Oh, and one other textbook. I'm sorry, I'm giving you 4, and at some point I'm gonna give you too much, and it's gonna be, almost not worthwhile. But okay, so one of the pioneers of convex optimization, and I'm restricting my recommendations to convex optimization, is this guy named Yuri Nesterov. So he developed an algorithm that, for a lot of settings, many of which discussed here, convex optimization, outperforms gradient descent in the worst case. So for certain function classes, it is optimal in some sense. There's a matching lower bound. I might touch on that on Friday. Hopefully, we'll really deep dive in. And that is called Lectures on Convex Optimization. It's by Yuri Nesterov, Y-U-R-I-I, Nesterov, Nesterov. I think that's a really wonderful resource. It's very straightforward and to the point, but it literally lays out all the stuff. Oh, and it also has really nice, it lays out all the properties of smoothness, strong convexity, the combinations there of anything you could want to show. It's been a nice resource. I think I will kill it at that, and I apologize to whoever's wonderful textbook I couldn't think of in real time. Hopefully they will see that and be like,
Thanks.
Yeah. Okay, so if that is, maybe I'll pause for one more second just to make sure, because I did go through a little bit lightning speed, some of the basic stuff, but it's important for you guys to understand that before we move on. Okay, so I'll depend on you to interrupt me if something else comes up. Please interrupt. So I'm going to do an example of a quadratic function. I will start you off with this example, but hold on, I have 10 minutes left. I'd rather take questions. This is going to take me longer than okay. So on the problems, I gave you guys essentially try and understand the behavior of SGD and stochastic gradient descent and gradient descent on quadratic functions. And one of the questions deals with the performance in this over-parameterized regime. And what I mean by that is in a context in which there are more solutions, there are an infinite number of solutions. And so what you'll find is that a lot of algorithms will have different, what they call inductive biases, which means that they will be predisposed to define certain kinds of solutions. And so very classically speaking, and I'll ask you guys to show this, is, for example, for a least squares problem or for a quadratic objective, gradient descent and stochastic gradient descent, if there are infinite number of solutions, so you're underdetermined, we'll tend to find the solutions that have minimum norm, L2 norm. that's a very classic property, and intuitions like this are being imported in the deep learning context where there are infinite numbers of solutions. You want to understand the inductive bias of your algorithm. So I think that's an interesting problem, priming you guys to think a little bit more expansively about how can I use these classic results for these nice settings and think about expanding them to more complicated settings. So it'll be interesting to see how you guys, what you think of some of these problems. But yeah, let me before, I think we'll dive way more into the detail, more sophisticated algorithms on Friday. And I'll just pause here and just make sure that there are no more questions, because yeah, with 8 minutes, I don't think I have time to go through an entirely different concept. I apologize about the dropout, guys. It was unexpected. Also unshare my screen.
Is it really an official Zoom lecture if someone doesn't have technical difficulties though?
Yeah, I had a lot when I first started Zoom, and then there was a stretch where I was doing wonderfully, and then yeah, the last 2 times it's been weird. So, okay. I hope everything was clear. I'm just going to pause again. I'll stick around if you guys have questions, and hopefully, be around to answer some of the questions you have with the problem exercise sheet. I remember there is a method to keep the depth steepness of the curve slows the algorithm down. How does it work? I think
I meant like when the curve is like really at the bottom, I guess like it's really like low.
Oh, shallow.
Shallow, sorry.
Okay,
that was what I was looking for you.
Yeah, yeah. Oh, interesting. Okay, so right. I think there are a couple of algorithms that could work there. So one thing I haven't touched on, and this was the Urey-Nesterov thing, is there is an algorithm that finds a solution faster if you are convex. And that might work well with bold examples, and that's called accelerated gradient descent or gradient descent with momentum. So that might be what you're referring to. I'm not quite sure. Yeah, there are a lot of tricks, and it depends on the structure of your objective function. So if you could formulate the kind of flatness into some sort of property, perhaps there's a way of designing an algorithm that would adjust this flatness property and not slow down. Sometimes normalizing the gradient also helps with that. Also, if you guys have any other things you would like for me to touch on Friday, if you can drop it in the Slack, and I will try and absorb, not as much time to prepare, but I'll try and absorb it so we can kind of at least brush upon the idea. Okay, and just to be clear, I just want to, okay, yeah, I'll be around, so please ping me or DM me, and I'll answer certain questions in private if you guys want to discuss, or if you don't want to chat publicly about certain misunderstandings. Please DM me. State the weights with a delta that is parallel to the gradient, but with magnitude inversely proportional to the gradient. Yeah. So this person is, I think you're discussing or suggesting that in this flatness regime, you want to normalize the gradient by dividing by the norm of the gradient. And I think that trick typically tends to work with flat objectives. Hopefully I've understood your proposed solution well. Delta is parallel to the gradient. Yeah, so, okay. It's unclear to, so someone mentioned adaptive methods. This is pretty sophisticated. It gets into kind of deep learning regimes. There are certain, so adaptive methods kind of help in a couple of regards. I'm not quite sure, maybe empirically with flatness, it helps, but I'm not quite sure if provably it helps with flatness, but I might be not up to date with the latest results with adaptivity. One thing is recently it was shown adaptive methods, and by adaptive, guys, I mean methods such as AdaGrad or some of these more sophisticated deep learning algorithms such as AdaGrad or ADAM or RMS prop. You may, if you've ever implemented a deep learning procedure, this might be like standard algorithms you can choose from in TensorFlow. And what they do is they simply scale the gradient by some, what they call a preconditioner. This is typically what's referred to as an adaptive method if you're following the chat. And so they have, they tend to have nice properties or good empirical behavior on a lot of objective functions, one of which might be flatness. So nice point. Yeah, I agree with Jing Dong's, hopefully I pronounced your name correctly, comment about the connection between these adaptive algorithms and adjusting to the flatness, not necessarily being as straightforward as far as I know, but perhaps not as up to date. Could be a recent paper that suggests otherwise. Well, I would, yeah, go on. Yes.
I think empirically there is some interesting results on the performance of adaptive method and just standard SGD, because people observe like different performance on different like learning tasks. I can't really recall whether it was like computer vision tasks or NLP tasks that adaptive method perform much better than SGD method usually, and for the other one, it's like the reverse. So there, I think some people are trying to reason like why the performance of the optimizer is task dependent, but I'm not quite sure if that has something to do with the landscape of different tasks.
Mm-hmm. No, absolutely. I actually think I wrote a paper actually on this. So at least the folklore, I contributed to this folklore of at least, so SGD being more appropriate for vision tasks and adaptivity being more prone to overfitting, but more suitable for NLP-based tasks. But again, I think there have been many papers written after with different kinds of theoretical results. And so I'm not quite clear if even the picture I painted with that paper 4 years ago still stands, as deep learning is kind of a lot of an art. It's hard to make it a science and give hard and fast rules, you know, with this task, use this algorithm. It's kind of evolving based on people trying different things and different conventions being adopted. So we're at the hour, but I would like to stick around and I would love to continue discussing some of this stuff with you guys. Seems like there's varying knowledge bases here, and so it'd be cool to, you know, discuss with, if any of you guys didn't understand anything, or if you really want to talk about what's going on with the state of the art stuff, I'd be happy to stick around. So yeah, or feel free to take a break. I'll stop.